in India. So thank you so much for the opportunity to speak at GT Square. So my name is Faiz. I'm a fourth year PhD student from BITS Pilani, Hyderabad campus, India. I'm working with Dr. Sharan Gopal, and today I'll be talking about solenoidal automorphisms and the periodic properties. I have given a quick link of the article on which this talk is based. So if you wish, you can go and check it out. And this work was funded by Department of Science and Technology, Government of India. So I move ahead with a way of just 1 minute. Something is out. Okay. So my institution and my department. So BITS Pilani, Hyderabad, established in 2008, and it's one of the premier technical science engineering colleges in India. And our department has currently 28 faculty members and around 50 PhD students pursuing their research in various disciplines. So the outline of my talk is I'll initially begin with more of a geometric insight, like what are dyadic solenoids, the most basic type of solenoid, moving ahead with some terminologies which will be useful in understanding. And I think I'm going to take a lot of time in terminologies. And later on, I'll talk about the solenoidal automorphism, especially one-dimensional case. And I'll try to conclude the talk if there is a lot of time left with higher dimensional solenoids. So we begin with the question that what is a dyadic solenoid? So a way to see or understand dyadic solenoid is that you have a very special donut. Let's say the outer one is of purple color, and you assume that its flavor is blackcurrant. Okay. So I have this wonderful donut with me. Then I feel like, why don't I have another donut with a different taste and of a different color? So like, fine. So let's get apple or some other flavor. So what do is that you cut the donut and you stretch it. So what happens when you stretch it? When you stretch it, obviously the diameter is going to decrease. So when the diameter decreases, the length increases. So what do? I wrap it twice inside the bigger donut. So I get a big donut, and inside that you get 2 times wrapping of the bigger donut. And this goes on at every stage. So now this goes on, and at every stage you get a different color. So somebody says that what's the most like beautiful or the tasty donut in the world? So I'll just say, just take the intersection of all of them and you have the best ever tasting donut in the world. So it's like, okay, so, but isn't that what's called a dyadic solenoid? And then I say, yeah, exactly. That's what I meant by it. So let's come to the math part of it. Okay. So we consider a solid torus. So that is T, which is S1, the unit circle, cross the disk, denoted by phi x, y. So phi is lying between 0 and 1. And as usual, x square plus y square is less than equal to 1. So we are fixing a lambda belonging to the set of real numbers such that lambda is lying in the interval 0 to half. Lambda is something like a scaling factor. So we define a self map on this solid torus F such that F is f of phi comma x comma y is 2 phi modulo 1 lambda x plus 1 by 2 cos 2 pi phi and lambda y plus half sine 2 pi phi. So if you notice the first coordinate, you can observe that on a unit circle, you are actually wrapping the donut twice. And then, so what happens here is that this map F is stretching by a factor of 2 in the direction of the unit circle, and it is contracting by a factor of lambda in the B2 direction. So I think if I give you how the cross section of the geometry looks, you'll be able to understand it more. So what is happening is that F wraps the image inside T. So let's go to the picture. Okay, see, what is happening here is that if you observe, you have T, the first donut, then F of T, the second donut, wrapped twice. And then you have F square T, wrapped again twice. So if you see, this is how the cross section will look on the top left. And So this goes on and on. So coming back to the previous slide. So yeah, this map F is stretching by a factor of 2, as I told, and F is wrapping the image inside T, and the image of Fn plus 1T is contained inside interior of Fn T. So when you take the set S intersection n equal to 0 to infinity, this is what we call as a dyadic solenoid. So in one way, if you think that at every stage we are wrapping it twice, so can we think of it or can we characterize it like we have a sequence, and at every stage it's going to tell that okay, I see. Is the raised hand a question, a
yes.
comment by Alex?
Could I see the definition of F again?
Yeah, sure.
Thank you.
Yeah.
Thanks.
Okay. So can you move ahead?
I just wanted to see it again. I couldn't see it properly the first time. Thanks.
Okay. So we move ahead. So this set S intersection equal to 0 to infinity, Fnt is a dyadic solenoid. So what I was thinking is that the characterization can be done like we have a sequence of positive integers, and every integer is greater than equal to 2. So why can't we multiply it like maybe with a number greater than 2? Let's say at first stage, I wrap it 3 times. And the next stage, I wrap it 5 times. And the next stage, I do it 7 times. So this motivates the definition of a general one-dimensional solenoid. Okay, so this is the cross section. And as you can see that when we get to the T intersection part, you get the best donut, best tasting donut in the world. Okay, so moving ahead. So I work in the area called topological dynamics, where I deal with the topological properties. So basically, we have a topological space, and we have a self map on the space. So we study various trajectories, the eventual behavior of periodic orbits, periodicity. Is that what I work with? So a dynamical system is a pair XF, where X is a topological space and F is a continuous self map on the space X. So given a point X belonging to this topological space, we look at this sequence. So the sequence is like X, F of X, F square X, and this moves by composition. So this sequence is called the trajectory of X. And so basically a point is known as a periodic point if it is returning to itself after a certain stage. So if Fn of X equal to X, where Fn stands for F of F composed with itself as a function n times. So if Fn of X equal to X for some n belonging to the set of natural numbers, so this point is known as a periodic point, and the least among such n is called known as the period of X. So the problem of characterizing the sets of periods and periodic points of a family have been well researched upon. So basically, I'm looking at two specific sets. So if you have a topological space X and curly F is a family of maps on the space X. So first we look at this collection. So this is set of all periodic points of set of all periods of F. So basically set of all natural numbers such that F has a periodic point of period n. And when you look at the next set, so we look at all PF, where set of all X belonging to the space X, where X is a periodic point of F. So basically in one set, we are characterizing all the points of the space, which are periodic points. And in the other set of periods, we are basically characterizing all the points which gives us a periodic point of period n for a specific function f. So the work on periodicity runs in these two sets for different spaces and for different maps. So moving ahead. So how do we formally define a solenoid? So a compact, connected, finite dimensional abelian group is called a solenoid. But there are equivalent alternate definitions of a solenoid. So equivalently, a topological group sigma is a solenoid if and only if its Pontryagin dual group sigma hat, that is how we denote the Pontryagin dual group, is isomorphic to a subgroup of the discrete additive group Qn. So basically, for now, you just assume that you have a group, topological group sigma, and we have something defined as a Pontryagin dual of that group called sigma hat. So when sigma hat is lying between Zn and Qn, we call it a solenoid. So now the question comes that what is a Pontryagin dual group? So basically a continuous homomorphism from a group to unit circle is called a character of G. And the set of all characters of that group, which is denoted by G hat, is called the Pontryagin dual of that group G. So a couple of examples to tell you that is the Pontryagin dual of Z, the set of all integers, is the unit circle. And in fact, if you take the Pontryagin dual of the unit circle, it gives us Z. So yeah, so using pointwise multiplication, this forms an abelian group. So there are right now right now still a lot of work is pending in this. So I'll just tell you a bit about what work has been done. So for the extreme left and the right ends, where sigma hat equal to Zn, so sigma is an n-dimensional torus. And for the right end, when sigma hat equal to Qn, it's called an n-dimensional full solenoid. And in between anything, it's called an arbitrary solenoid or a general solenoid of n dimension. Okay. So moving ahead, so first we look at solenoid. So basically, one-dimensional solenoids are defined using the concept of inverse limit. So first I define what's an inverse limit. So we have xk, which is a topological space for every k belonging to n naught, that is set of natural numbers union 0. And we have a map fk going from xk to xk minus 1. I mean, so if you see the map is going in the reverse direction, fk is a map from xk to xk minus 1. And this is a continuous map. Okay, I think somebody has raised a hand. Yes, Andrew.
I think it's just...
Yeah, it was my previous question, but no, I don't have a question right now.
I'm sorry, I couldn't get you. Like,
I think you can keep going, Faiz.
Okay.
I have a question actually.
Yeah, sure.
So you define the definition of a solenoid on the previous slide.
Yeah.
Is there a classification of compact, connected, finite dimensional abelian groups? Like the Pontryagin duals just range between Zn and Q to the n. Do they?
Yes.
Do the groups themselves have a classification?
So what do you exactly mean
Like
classification?
Like how much do you know about the structure of these groups? Are they like products of the torus and a finite group or something?
Okay, so I think you'll get the answer maybe during the talk.
Okay.
Yeah, I mean, I'm going to talk about that, how to classify and get hold of the solenoids, like how are we going to characterize. So it's coming ahead, you need to wait a bit.
Okay, sorry.
Yeah. So, okay, so yeah. So we have this inverse map, inverse limit proceeding in the reverse direction. So we have this subspace, which is the product of fk's, defined as a limit xk fk. So basically you have this sequence where product xk belongs to the product of xk's. So this sequence where xk minus 1 is fk of xk. So basically, if you see that when we look at a sequence, usually what happens is that the current term defines the next term. But when you have an inverse limit, it goes in the opposite way. So as you can see that xk minus 1 is being defined by fk of xk. So it actually runs in the opposite direction. So when you have this collection is called the inverse limit of the sequence of maps fk. So now when, so basically I would like to point out that when we were characterizing solenoid as sigma hat lying between Zn and Qn, the definition of inverse limits defined in this particular way only works for the case n equal to 1 for one-dimensional solenoids. So for one-dimensional solenoid, if capital A denotes the sequence of integers, so that's what I was talking about, that instead of wrapping it twice at every stage, I start wrapping it arbitrarily. So we have A1, A2, and so on up, which is a sequence of integers such that ak is greater than or equal to 2 for every k belong to n. So the solenoid corresponding to this specific sequence A. So basically the dyadic solenoid, which I had shown you, corresponds to the specific sequence A equal to constant sequence 2, 2, 2, 2, 2, and so on. But the general solenoid denoted by sigma is xk belonging to the product of unit circles. So this xk minus 1 is ak xk modulo 1. So basically ak is denoting how many times the wrapping is occurring at each stage. So moving ahead. So now the question is that what is the relation between both descriptions? That is how when I have defined it using the Pontryagin dual and when I'm defining it using the inverse limit. So the dual of a one-dimensional solenoid sigma A denoted by the sequence A equal to AKs is isomorphic to the subgroup of Q generated by this initial product of elements from the sequence 1 by A1, A2, so on up to AK. So this is the relation between these two. Moving ahead. So a couple of more definitions and terms we would like to require to understand it. So S be an arbitrary subset of the set of rational numbers, and X is a term belonging to this set S. So for an arbitrary prime P, the P height of X with respect to this set S is denoted by HPSX and is defined as the largest non-negative integer n if it exists, such that X by P to the power n belongs to S. So one way to understand is that suppose my S is set of integers, and if I take any prime P, let's say I take the prime P equal to 2. So if I want to find out the P height of 1, the moment I divide it by any prime, let's say 1 by 2 or 1 by 3, so that is not going to stay inside our set S equal to Z. So I began with the set S equal to Z, which is a subset of Q. So, but if you take, let us say, the set of all dyadic integers, so dyadic integers can be defined as all the rational numbers of the form alpha by 2 to the power k. So in that case, you can keep on dividing by 2 and still the element stays inside that set. So here basically what we are trying to find out is that how much a prime can be divided inside so that the element is staying inside the set. So basically, if you have a finite value of it, if it exists, so if we say that this specific number is the p height. But if we don't have a finite value of it, we define the p height of that element to be infinity. So when we, for different primes, we actually have a sequence HPSX where P is ranging all over the prime numbers in the usual orders and with values in n0 union infinity. So we call this, we call such sequences as height sequence. So the question is, why do we need height sequences? So we need height sequence is that when we are working with the case n equal to 1. So basically our solenoid Pontryagin dual group sigma hat is lying between Z and Q. So if sigma hat is an arbitrary subgroup of Q containing Z, I should have a way how to characterize it. So we characterize it basically using height sequences. So if UP and VP are two height sequences, such that they are equal to same for all but finitely many primes. And if one of them is infinity at a specific prime, the other one is also infinity at that specific prime. So then these two height sequences are said to be equivalent. So if S is a subgroup of Q, so every subgroup of Q has a unique height sequence up to the equivalence as defined above, associated to all the non-zero elements of S. And if two subgroups of Q are isomorphic, that means that their if and only if condition, their associated height sequences are equivalent. So one good way to check whether, I mean, if you want to, let's say that, let's say 2Z, and no, not 2Z is a bad example. Let's say Z 1 by 2Z, like I take Z in all the midpoints, and then I want to see if it is isomorphic with some other group. So you can just calculate the height sequence and find out if they are equivalent in some way or not. So this is the characterization for the one-dimensional case is given using this height sequence. Okay, so a couple of more terminologies which I'll be using for the result is that let QP and ZP denote the field of periodic numbers and the ring of periodic integers respectively. So we have the periodic norm. UP denotes the periodic norm. So basically for any rational number A by B, just pull out all the primes which are inside A and B. So if you have the number A by B, it's P to the power alpha into, let us say, gamma by theta. So the periodic norm of that number is 1 by P to the power gamma. So I kind of assume that you are familiar with the periodic norm. And so we have this NPS, which is supremum of all the P height values, and ZP star is the multiplicative group. So basically we have set of all elements in ZP such that their periodic norm equal to 1. So basically the information whether NPS is going to be finite or not for a given prime is going to decide what will happen with the solenoid. So one more definition is that D infinity S is set of all primes where P height is that P height of NPS is infinity. So if you see in the case of dyadic solenoids, you can divide as many 2's you want in the denominator. So if I'm talking about the dyadic solenoid, we should have 2 as one of those primes, which is give us the P height to be infinity. So yeah, so a little bit of digression. So these two results were proved by Sharan and Raja in 2017. So they gave a characterization. So basically what they did is that they have done it for both the extreme ends. For n-dimensional torus, which is the sigma hat equal to Zn and sigma hat equal to Qn, and they did it for one-dimensional case. But all the characterization was done using Pontryagin dual. So these are the two results where first he describes the solenoid, and in the second he describes the periodic points. So my work is based upon doing the characterization in terms of inverse limit using height sequences. So okay, so here's the difficulty in doing it further. So the above characterization depends upon the descriptions of all the subgroups of Q using the notion of P heights. However, no such description is available for the subgroups of Qn for n is greater than or equal to 1. In fact, Kekris in this article says that there is probably no reasonably simple classification of these groups. In fact, I tried to find a lot and I went through some articles also, but I couldn't find any reasonable or an simple way to characterize all the subgroups of Qn for n strictly greater than 1. Also, in other words, I can say that if I would have had a characterization, this problem would have been complete for now. Okay, so so these are the results which I have got for dealing with the solenoid as an inverse limit. So we have sigma A, which is a one-dimensional solenoid, and S, which is the Pontryagin dual of this solenoid. So where A is denoting a sequence. So P is a prime number, and we denote NP of S, that's the P height. NPS is defined as the supremum of HPX. So we denote NP S as NP. So it says that P belongs to D infinity S if and only if for every J belongings to the set of natural numbers, such that there exists a K belonging to the set of natural numbers, such that P to the power J is dividing an initial sequence of product of terms from the sequence of the solenoid. So in other words, you can also see that P is dividing infinitely many of them. And if P is not dividing the terms in D, sorry, my bad. P is not in D infinity S. So we have NP, which is some largest integer, such that P to the power NP divides this product of AKs for some K. So basically, this is a result. Let me go back. So if you can see, Sharan and Raja have done it for P belongs to D infinity union infinity, and P does not belongs to D infinity union infinity. And then he has these two characterization of UP. So similarly, we have obtained the two conditions. And moving ahead, so F is an, so basically what, for a dynamical system, I already told you that we have X, which is a topological space, and we have a map, self map. So currently we are dealing only with automorphisms. So if F is an automorphism on this one-dimensional solenoid, so its dual is an automorphism of a subgroup of Q. So every automorphism is induced basically by a non-zero rational number alpha by beta. So for any xk, the sequence of xk's belonging to the solenoid sigma, we defined product of f of sequence of fk's is by multiplication with this non-zero rational number alpha by beta. So there is a, so what we make without a flash of generality, we make an assumption that a equal to beta of, we just replace this sequence of a equal to ak's as a equal to beta of bk's. So we have the condition that bk and beta are co-prime with each other. So this helps us to pull out the beta from the denominator, and everything goes to the numerator. So as you can see that f of xk changes to alpha beta 1 x1 alpha beta 2 x2 for each xk, but the solenoid is same and the sequence changes to beta of bk's. So there are some more results which we found out. So I'll not go much into them. So it's just for you to have a quick look. And can somebody let me know how much time do I have with me?
You've still got about 10 minutes.
Okay, thank you. So here we again have a sigma is a one-dimensional solenoid where a equal to the sequence AKs, S is the dual of this solenoid. So this sequence XKs, I just denoted by UK by VK. And these are all rational numbers. And I'm taking them to be co-prime. So basically, what we obtained is that after, see, H is the least integer such that CH is greater than or equal to 0. So for every K which is greater than H, this CK can be written in terms of the previous terms, basically. So, and the next thing is that if xk is periodic in sigma phi, where phi is an automorphism of sigma a induced by alpha by beta, then basically every coordinate is a rational number for every k belongs to n naught. And further, we also obtained this result that if P is in the set D infinity S, then the periodic norm of every coordinate is less than or equal to 1. So these are two observations which we made in the way. So now we come to the main theorem. So the main theorem is phi be an automorphism of the one-dimensional solenoid induced by this non-zero rational number alpha by beta. So I'm just replacing the sequence A instead of AKs as beta BKs, where the condition of co-primeness is again there with beta. So for each L belonging to N, I define UL. So UL is a intersection of 1 by P to the power EPL ZP. ZP, I think I defined ZP before using periodic integers, intersection Q, intersection S1. So this P to the power EPL, which we have got, is defined as 1 by alpha to the power L minus beta to the power L, and you take the periodic norm of it. So this, and we have a map gamma KL from UL to UL, and this is the map defined as gamma KL of X is beta BKX modulo 1, the solenoid map. So for each K belongs to N and L belongs to N. So then the periodic points of this automorphism phi is basically L equal to 1 to infinity given by the inverse limit UL and gamma KL. So UL is defined here and gamma KL is defined using the sequence beta BKs. So the set of all periodic points is given. And on that, I would like to make a remark. And I have shared the article on which this talk is based. So you can find a proof of this theorem there. So UL is the subgroup of S1, that is the unit circle. And this map gamma KL is the restriction of gamma K to UL. So gamma K is map on S1. So this solenoid is basically sigma NBK is an inverse limit of S1 gamma K. And then we are further restricting gamma K to the UL, where UL is a space defined above. So it's like you just restrict maps to achieve the final set of periodic points you wish to get. So here we move to the next result. So let phi is an automorphism of one-dimensional solenoid sigma induced by alpha by beta. And EPL is the one which I defined in the previous slide, 1 by alpha to the power L minus beta to the power L periodic norm. So then the number of periodic points of phi. So basically in the previous results, we gave the set of all periodic points. And in this results, we actually counted the number of periodic points with a period L. So if you like want to say, I want to know for a specific, let's say, I want to know how many periodic points will be there for a period, let's say 23. So this will give you all the exact count. And this result, the exact count which we have got. So the above theorem about the number of periodic points is in accordance with a similar result proved by Richard Miles in 2008. So he had done work on endomorphisms on solenoid and related groups. So he had also obtained this count for periodic number of points, but he had done it for endomorphisms, and using a different method. So moving ahead, we now extend our result for periodic points to some automorphisms of certain higher dimensional solenoids. So basically what has been done is that the one-dimensional case was completely characterized using inverse limits, using Pontryagin dual also. So now we make an attempt to see if we can do it for the higher dimension case, because right now we don't have any classification of all the subgroups of QN. So this gave us an idea that why don't we look at those n-dimensional solenoids which are conjugate. Conjugate is something like, let's say, isomorphic or homeomorphic in weight terms. So we look at those n-dimensional solenoids which are conjugate to the product of n one-dimensional solenoids. So it's basically like having n copies of one-dimensional solenoids and using that to create an n-dimensional solenoid. So this is how it is defined. So for a positive integer n greater than or equal to 1, we have a map pi n, which is from Rn to Tn. So this is a homomorphism defined in the following manner. So now, instead of taking just sequence of integers, when we go to the higher dimension, we have to end up taking sequence of n cross n matrices to basically define the solenoids on higher dimension. So we have M bar, which is a sequence of n cross n matrices, and we have integer entries and non-zero determinant. So an n-dimensional solenoid sigma M bar is defined as, again, here we are using the concept of inverse limit. So basically xk minus 1 is pi of n mk xk, in a similar manner how it was defined for one-dimensional solenoids. So in other words, sigma M bar, which is the n-dimensional solenoid, is defined as an inverse limit. And this map delta k is a map from Tn. So Tn is the n-dimensional torus, or you can say S1 cross S1 n times. So this is defined as delta k of x as pi n mkx. So this is the result which we have obtained for this. So a lot of construction goes like, constructing diagonal, taking. So we have basically what we did for n-dimensional solenoids, which are occurring as a copy of one-dimensional solenoid, n copies of one-dimensional solenoid. So basically what we have, I'll just give you a rough idea. So we had n different sequences. So we tried to actually construct matrices of order n cross n using these specific different n sequences. So we use the concept of just taking the diagonal and doing it. So in the article, you'll find the whole process, how we have done it. So this space for each L belongs to n, we define a VL, and product of I equal to 1 to n. So there are n copies of intersection of these spaces. So we have P EPLIA again as 1 by alpha IL minus beta IL, periodic norm of that. And then delta KL is a map defined as delta KLX, pi and MKX. So then at the end, finally, you get the set of all periodic points of the automorphism phi. And this automorphism also takes help of automorphisms on individual coordinate or individual solenoids. So I'm just giving you this direct, like the consistent result or the gist of it. So periodic points of this automorphism phi is inverse limit of VL delta KL. And again, we have this restriction that VL is a subgroup of Tn, delta KL is the restriction of delta K to VL, where each delta K is a map on Tn such that sigma M bar equal to inverse limit of Tn delta Ks. So right now, currently, I am working on those solenoids which are algebraic number fields. So basically what happens is that when I take a finite extension of Q, so it's like, right now I'm working on simple extension or algebraic number fields. So I'm just doing the same work for those solenoids which occur as, let us say, sigma equal to Q of some C. So that work I'm doing using ADILs. So right now, the problem is in process, like I'm right now working on it, and still I'm looking for a good classification, let us say for n equal to 2, n equal to 3, for all the subgroups of it. Or maybe if you can, just not taking like product of subgroups in 2 coordinates, but something which can help us to pull out all the subgroups of specific, let's say the case subgroups of Q2 of some specific order. So that is also another direction of work in which the periodic points can be characterized. So yeah, the talk went more technical towards the end, but yeah,